Okay, hello again, students. So we sort of looked at the Gaussian distribution here a bit in the last video, ran some mathematical plots to see what it looks like, but that's sort of what the functional form would be. The uniform distribution, I don't have a lot to say about it, but it's sort of defined like this. It's something like this. It's has sort of a split definition here. So it just sort of says that, look, as long as you're between the range of interest for you here, between limits b and a, will give you sort of a 1 in b minus a chance of hitting that number, as long as you're in there, and you're sort of zero otherwise. And so the distribution would look something like this if you had like a big x-axis like this here. Here's limit a right here, and here's limit b right here. And so if you wanted to divide this up into bins or little categories like that, then as you can see here, each bin has a 1 over this with probability of occurring, right? And so if you get 5 in a bin like that's a very constant probability, so long as B and A sort of stay set, which they must. So in any given bin, if I get 1, 2, 3 in this bin, well, I better get 3 in this bin, and I better get 3 in this bin, and 3 in this bin, and 3 in all the bins. And that's just the way the uniform distribution works. So this would be something like, once again, I mentioned, like a dice would work this way, right? Because you have an equally likely chance for a fair dice for getting the numbers between 1 and 6. And so that's sort of what that would be. We won't encounter that in Physics 340 at all, but I love these distributions, so I just thought I would tell you a little bit about them. The one you will encounter, which I'll just sort of leave you on your own to grapple with when the lab comes up, we'll have a little review on it next week, is the poisson, though. And the Poisson distribution becomes important because we use it when we are talking about Gaussian or normally distributed data, but where the average value starts to become very small. And the question about the smallness here is something like this. You know that the Gaussian sort of looks something like this, maybe if you have sort of a nice healthy average of 20 like that. But the issue is that the average becomes very, very small. What do you start to do with the Gaussian? As I'll even draw in reverse here, as it starts to butt up against 0 right here, right? Like this might have an average value of like 2 or something like that. And so the question is, well, what do you do in this region right here? Because you don't want to go negative, like you don't have any negative data points. Like if you keep calculating the charge of an electron or the length of a piece of wood, you won't get negative values for that. So how a Gaussian sort of butts up against the y-axis is a bit of a question right here, but we use the Poisson approximation instead when that happens. And the Poisson just has a function like this. It's in the back cover of your book. It's always a function of sort of some funny Greek letters here. I'm not sure exactly why. That's just sort of convention. It's going to be equal to e to the minus mu to the new power. And in the very bottom here, we have mu factorial. And so it's just a very funny function. I'll just sort of let you look at it a little bit, but just keep in mind here that the mu here, this is your average value. So it's like the capital X in the Gaussian. Average value here, and we'll say is always usually kind of small, 2, 1, 0, something like that. Okay? And nu here, this is your independent variable. This is the one you might be asking some question about what is the chance of getting a certain data point in my experiment here. And you just sort of notice here that the way it's sort of bound up, students always need to be careful with this term here, because once the average is chosen, this is just a constant here. So you're not plotting e to the minus x, you're plotting e to the minus mu, but mu is a constant. It's just the average you've chosen for your distribution here. And then you raise that average to the nth power and take nu factorial in there. And nu, of course, is your independent variable. So this is the fraction that's going to change, say, as you run a plot of the Poisson or something like that. And so just wanted to say a couple things about it also. Because down here you have this factorial, remember, technically the factorial only works for integers. So that means you can really only take like 2 factorial or 3 factorial. It wouldn't really be proper to say 2.2 factorial, although the gamma function does allow that to happen. But my reason for telling you that is the Poisson then is a discrete distribution. Okay, discrete distribution, and by that, it really only strictly has to do with counts of things, because you can only have 1 of something, you can only have 2 of something, or 5 of something. You can't say have 5.2 people coming into your ice cream shop statistically, that kind of thing. And so the Poisson distribution has some absolutely wonderful applications out there it's even something worth Googling, for example here. But the first time it was seen, believe it or not, was horse kicks in the Prussian army. So I don't remember if it was for soldiers that died or just got kicked by horses, but once in a while when they're out there in the field doing their thing or whatever, once in a while one person will get kicked by a horse. Then for the next couple of days, no one will get kicked by a horse. Then suddenly 2 people will get kicked by a horse. And maybe one day 5 will get kicked by a horse. But the point is that you might start to wonder here, what is the pattern in data like this? And it will be the Poisson distribution. Something like this will be the Poisson. I don't remember where I wrote Poisson. I'm trying to go all the way up here. So the pattern in data like this will be the Poisson distribution, okay? And the Poisson distribution has a lot more application, like in tire defects, and people in a room. If you just went on a room on campus or something and waited for the number of people that would come in a room, you'd also get something that's the Poisson distribution. So I'm going to wrap this video up here just in short order, but quickly. The Poisson distribution, it looks very much like a Gaussian, but it's often very asymmetric like this. So it sort of looks like something like that. So very asymmetric. I'm so used to drawing Gaussians that I'm even making this look more symmetric than it needs to be. So in other words, the Poisson has this shape here of always having sort of a low average right here. So the mu would be right here, a very low average. But then there can be sort of more points over in this region right here than would be over there. But it definitely handles the more graceful butt up against the y-axis right here. But remember, it's also a discrete distribution, so it really isn't correct to me to draw this smooth curve like that. What I really should do is say, okay, the Poisson is discrete. There's going to be so many events here, so many events here, so many events here, so many events here, so many events there, and that's about it. It's a discrete distribution, so there wouldn't be anything in between some fractional value like that. Okay, so those are the 3 common distributions. Once again, you have the Gaussian, which everyone's familiar with, the bell-shaped curve, the uniform, where everything is equally likely, and the Poisson distribution, which is like a bell-shaped curve, but for low averages and has a definite asymmetric capability, or characteristic is a better word. And so this is something that Poisson will grapple with. In our first nuclear counting lab, we will see both Gaussian and Poisson distributed data, and you'll be making plots and histograms of both of them.